Hi, this is Vinay. I am a PhD student at the Institute of Mathematical Sciences, Chennai. My poster is about studying the influence of thermalization protocol on Poiseuille flow of confined soft glass. This work has been done with my PhD advisor, Pinaki Chaudhary. Also, this work has been published recently. You can refer this for more details. Poiseuille flow is a type of flow happening in a confined channel or pipe because of some externally applied pressure gradient. In this schematic, there is a confinement along the g direction and there is a flow along the x direction, which imposes a stress field across the channel, resulting into a velocity profile. The nature of velocity profile is parabolic when the liquid is Newtonian, while when the liquid is non-Newtonian like glass, then these velocity profiles become blunt. We have used here molecular dynamic simulation using 80-20 linear Jones binding mixture at temperature 0.4 confined via walls. Here the control parameter is applied forcing restraint which causes the flow. Here we have used a channel width of 100. We have used two different thermalization protocols to remove the excess heat produced due to the flow. In the first implementation, we use wall thermostat where the atoms making the walls are vibrating around their initial position and their temperature is maintained. Such thermal wall control the temperature of the fluid. And also, such implementations are close to many real-life applications and experiments, since there is a flow of heat from the central region towards the wall, so there is a non-uniform variation of temperature in the channel. While in the another implementation, we use DPD thermostat to directly thermostat the fluid particles while the wall particles are frozen. So here the temperature is uniform across the channel. So the important point to note here is in the case of wall thermostat, simultaneous presence of local temperature gradient and stress gradient due to the flow. So the question is how the two thermalization protocols that we have discussed here affect the flow behavior of a glassy liquid. First, we try to understand in the case of two thermostat implementations what happens in the absence of flow. So here we see there is similar thermal and structural behavior. Also, in the presence of flow, in the case of wall thermostat, as we already discussed, there is a non-uniform temperature variation and there is a uniform temperature variation in the case of DPD thermostat, while the density and the stress behavior is almost similar in both the cases. So here, although there is a non-identical thermal conditions, but similar structural properties are there. Also, we have measured the velocity profile in both the thermostat implementations. So here, the velocity at the center in the central region is higher in the case of wall thermostat than the DPD thermostat. Also, this region is narrower in wall thermostat. As a result, shear rate, which is nothing but the spatial derivative of the velocity, is also different in both the cases. Also, we have measured using the stress profile and shear rate profile to plot stress versus shear rate, which called flow curve. Here, in the case of wall thermostat, there are different branches of the flow curve for different forcing strengths, but for the case of DPD thermostat, all these different branches collapse on a master curve which can be further fitted with Herschel-Buckley type of form. Also, we have done comparison of flow curves to the Quate flow measurements, which I am not showing here. We have also tried to understand the transient behavior where for a given forcing strength for different waiting times we try to measure different quantities. The red solid line that you are seeing here is actually the steady state response. Also, we have tried to measure the mean flow velocity of the for different forcing strengths in the two cases. Here we see that mean flow velocity is higher in the case of wall thermostat than the DPD thermostat. Also, the steady behavior reached from the quiescent state is earlier for the case of wall thermostat than the DPD thermostat, and this onset time scale of the steady state for the flow is actually plotted here, and this can be further fitted with power law behavior. Just to summarize, here we have studied the steady and the transient response in two different thermalization protocols. And we have also done different comparisons with the quaid flow, and also we have tried to study the effect of changing the channel width. These results are not shown here, but you can discuss these results and also different aspects when you visit my poster. So thanks for your attention.